5.2, exact area and the definite integral. We saw before with this example, this is x squared again from 0 to 2, and we'd like to try to find the area between the curve x squared and the x-axis over this interval. Now, there is a way to describe this in notation, and that is with these symbols here, the integral from 0 to 2 of some function, in this case we're talking about x squared dx. Okay? So this is the exact area we were talking about here. The symbols that describe it. Okay? So in general, the definite integral over an interval AB of some function times dx is the net area between f of x and x-axis over the interval AB. So ours is specifically x squared, and the interval is specifically 0 to 2. But this integral symbol is what's used to describe this area. Right? I haven't defined exactly what this is mathematically, just in terms of conceptually what is it is this area right in here that we're talking about right now. Okay? All right. We saw when we computed L4 and R4, we computed the left endpoint approximation with 4 rectangles and the right endpoint approximation with 4 rectangles in the previous examples. We saw that L4 was 1.75. And R4 was 3.25. And we noted the actual area, because of the way the pictures looked, was the actual area would be between. That was noted in those examples. So in other words, the actual area, which is this set of symbols, right, with the particular function and interval substituted in, it means we could write right now that 1.75 is certainly a value lower than the definite integral we're talking about, the actual area. And 3.25 is a value larger for sure. So now let's look at the 3.25 R4 value back again pictorially for just a moment. So what we had before was, if we're using right endpoints, so over the first interval, go to the right endpoint and go up, and that generated a rectangle height. We did that for all 4 of the intervals. Went to the right side of the interval, right endpoint, and we generated rectangles so as to approximate the area between the curve and the x-axis. So when we computed R4, this whole area, the green plus the extra white area here, the over approximation, gave us the 3.25 value, which was too much. But it's pretty clear if we increase the number of rectangles. In this case, let's just go to R16 for a second. We'll just start to fill in what that should look like here. So if we went up to R16, 4 times the number of rectangles as before, right? So within each one of these, there should be 4 additional rectangles. So if you did that, then on the right side of each interval, right, 1, 2, 3, 4 on the right side, you map up, go across, map up, go across, and so forth. Yeah. This one's already there in a sense. Just keep going like that. There we go. And keep going again. So for each one of the 4 subintervals within each of the rectangles now, right, you have 4 new rectangles there. And where am I? Here we go. There. All right. So R16 would look something like this. And clearly, right, the shaded in blue region now is much less than the white region, right? I mean the white and the green together, and thereby making the approximation better. Right? It's pretty clear this would be better than the R4 approximation of 3.25. It's surely a lesser value and closer to the actual green area value because each of the over approximations is much less than it was originally, right? We subtracted off, in a sense, all of these leftover white areas from the 3.25, giving us an even better approximation to the actual green area value. Okay? So this gives us some sort of intuitive sense that if we were to keep increasing the number of rectangles, the error away from the actual value of the area, that is the green area, would be much less, right? And therefore our computation using more rectangles would be more precise and closer to the actual value. So this gives us some sort of intuitive notion of what we should do with our Riemann sums. Again, that's surely a better approximation than what we started with R4. Right? So down here, we don't want to compute R16, but we want to take it the ideal way that if we had the limit as n approaches infinity, again, where n is the number of rectangles, of our Riemann sum, right? Again, I'll use the right endpoint expression. So again, without the limit, here is a regular right endpoint expression, right? This is just Rn. But if we let n go to infinity, which again, n is the number of rectangles, so if we let the number of rectangles approach infinity, we should get closer and closer values to the actual area. And therefore, if we actually took the limit to infinity, we should get the exact area under the curve.